Okay, so today we're going to be playing with some of the what we call identities or relationships that exist between these trig functions. Now again, since we're playing with things that are like fundamental shapes, right, a triangle and a circle, all sorts of interconnection is going to happen. And by that I mean connections between things that you might not have expected or that seem to be repetitive or just variations on a theme. Which makes sense because we're kind of going around and around in a circle, right? If we're on the unit circle, and the red, which is the cosine, maps the horizontal distance, and the black maps the height on this circle as we go around and around, then some repetitive stuff's going to happen, and there's going to be a lot of patterns. So I just say that to kind of underscore all the different parallels and connections you'll see with these problems. So first of all, to bring about and into our sight line here, the tangent function, which we looked at last time, which we know is the graph of sine over cosine. And maybe we could see from here, let me change my, oh, I don't need to change you, change my graph here to be in radians. And we can start to see some of the patterns that we know to be true. First is that sine travels between 0 and 1, starting at 0, making the output, since tan x is really, let's say this. Let's see, these are indistinguishable over cos x. Right. So since the y value is 0 at 0, that means this tangent curve is going to be 0. And then when we scoot towards values where cosine, the red function, is 0, we're going to have a vertical asymptote, right, where it shoots off to infinity. And since this keeps happening as we go around and around, that's going to keep happening. So every odd multiple of pi over 2, we see those vertical asymptotes, so it has a length period of pi. So that's the connection between tangent, sine, and cosine. Now there are some nice connections between sine and cosine themselves, and then we have some other functions that emanate from just playing around with these three. Okay, so the first that I want to show you is that sine and cosine, and I've said this before kind of in passing, but sine and cosine really are just each other shifted by 90 degrees. You can see it in the wave, and if I change this to be minus some a value, so we'll give it a horizontal shift, and I shift it by 90 degrees, which is about pi over 2. Can I change this here? Let's see. 0 to 5, let's say. Shifted at 90 degrees, so that'd be from 0, pi over 4, pi over 2. You see they're sitting on top of each other. So they are really very closely connected in that way. Why is it 90 degrees? Well, one way you could kind of think about it is if we put the unit circle back up and you were sitting right here at the starting position. If we had just rotated it 90 degrees and we were sitting up here, well, now the height is your horizontal distance, right? And your vertical distance is your horizontal distance. It's kind of just taking the Ferris wheel and turning it 90 degrees. So that's why the same pattern is going to emerge. So sine and cosine really are just each other rotated 90 degrees. So you get a lot of nice equivalences from that, right? So instead of writing, for example, if I had sine of pi, I could instead write this as cosine of pi minus pi over 2, right? Which we know would be actually the same as cos of pi over 2. Now I'm choosing simple values here, but let's think of that. What's happening? So sine of pi sine is the black curve, this is the one we're on, is 0. And that's going to be equal to cosine of pi over 2, which we know cosine of pi over 2 is 0. It sits right here. And this is going to hold for every single value. So there are times, especially in calculus, when we would rather switch from talking about something in terms of sine to cosine. So anything we deal with waves, if we want to change, just like rewriting an algebraic expression, sometimes we'd rather write in terms of one function or the other. So this is one of those identities that we would use. So given an angle, x, this equals cos of x minus pi over 2 for any x. Okay? Well, that's broken. So that's one nice thing. And the same is true for sine and cosine. So it's just reversed. So you can add it instead of subtracting it. And so some nice things go along with that, and I'll jot those up on the tablet in a moment. But while we're here, I wanted to take a look at the other functions that emanate from sine and cosine. So if we're talking now about the distance on the circle, vertical and horizontal, what if we were talking about the reciprocal of that? Okay, so the multiplicative reciprocal, that's a tough one to say, which we mean the inverse, 1 over sine. So let's say I came up with some function 1 over sine x. This would also emanate some sort of period, but it doesn't look like tangent, right? It does and it doesn't. It definitely has asymptotes. And let's think about this thing's values. So if I take a table of values here, so let me do this, copy this and make a table out of it. So for x values like 0, pi over 2, why don't you like that? Because there's two f's. There we go. So something like this. We can maybe start to see the connection between this, which we call the secant of x, or rather, this is the cosecant. That's going to confuse people. This is the cosecant of x. It's the inverse of sine, and we see that it lines up with sine at these certain points. But then when sine hits 0, what happens? Well, if it's a reciprocal, it's trying to divide by 0, so it's going to shoot off to either negative infinity or positive infinity. But then when sine is equal to 1 or negative 1, well, 1 over 1 and 1 over negative 1, those are nice values. Those are equal to 1 and negative 1. So it keeps popping back up to kind of get a breath of air at 1 and negative 1, and then shoots back off to infinity because sine's going to be 0 again soon. Right? I can turn this guy off because he's not relevant. So this is what we call the cosecant, and this should be programmed in here, cosecant of x. And so it has regular asymptotes. It is still technically 2 pi periodic, since it has one cycle like this, one half cycle like this, and then repeats this pattern. So it is 2 pi periodic. But it has vertical asymptotes at every multiple of pi. Okay, so this is what we call cosecant x, and it's defined to be 1 over sine x. So it doesn't like that, but that's okay. But this is where the graph comes from, and just with some basic knowledge of fractions, you can make sense of why it has the shape it does. So cosecant comes from sine. All right, cosecant comes from sine. Now, the other one that comes from cosine, which we will now subtract out the stuff, come back here, and we'll turn off that graph. Great. So here with our cosine curve, in blue, we have what's called the secant, which is exactly the same. It's the reciprocal, or the flip, of cosine. What does it do? Same thing. Every time cosine takes on 1 or -1, it comes up and takes on that value as well, because it's 1 over that number. And then whenever it hits 0, pi over 2, 3 pi over 2, it has the same problem that tangent does, right? Which is having cosine on the bottom. So it shoots off to infinity here, 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 and here, and so on and so forth. So secant is this reciprocal function. Again, it's got that weirdness with being 2 pi periodic. However, its period starts kind of back here at -pi over 2. You could also, you could cut it up however you'd like, but when we get to inverting these things, we're going to want to make sure that it passes the horizontal line test, which these ones are going to have a bit of a dance to do that. But we'll get there in the next section. For now, I just wanted to show you where these come from and how they tie into the graphs that you already know. You might see this graph of cosecant and be like, where the heck did this come from? Or secant. That's the second time I did that. So the graph of secant and say, where the heck did this come from? Well, if you graph cosine and you know about its relationship here, then it should make a ton of sense. So we have secant, we have cosecant, sine and cosine, so they each have their own reciprocal kind of partner or cousin that's tied to them. And then for tangent, there's also the reciprocal of tangent. Now, what's this going to look like? If we think about, let's turn this into a table. Pi. Okay, maybe we need some more subdivisions in here, so over 4, 3 pi over 4. All right, something like this. And we'll go in the reverse direction to -pi over 4 and -pi over 2, obviously undefined there. So we've got some points plotted on here to give us a sense. Now when we reciprocate, meaning take 1 over tangent, what's going to happen? Well, it should flip with these values where it's 1 and -1. It should definitely be at those points as well. But what's going to happen when it's 0? What's going to happen when it takes on these asymptotes? Let's take a look. So if we call this q of x equals 1 over tangent of x, what do we see? Okay, it does meet at 1 and -1. Let's change the color. That's confusing. So green is cotangent. So it meets at those points of 1 and -1. At the places where tangent had vertical asymptotes, what do we see is happening with cotangent? Well, it had 0 on the bottom, right? So it was undefined. That's why it has a vertical asymptote. But now if we flip it upside down, it's 0 on top. So that makes it cross the x-axis. So if I drop out tangent, maybe that'd be a bit easier to see here. So see, it's taken on kind of this reverse direction here, crossing the x-axis where tangent had vertical asymptotes and shooting off to infinity where sine has takes on the 0 values. Because what is 1 over tangent really? 1 over tangent is really the flip of sine over cosine, which is cosine over sine x. So this is the graph of cotangent x. They're one and the same. Okay, so we have these first basic kind of building blocks of just the height and the distance on a circle. We know these are closely related by just shifting them over by 90 degrees. We see tangent comes into play if we take the ratio of them. And then if we start to flip these things, we get these new different functions that are used in a bunch of different applications. Again, we use these shapes to mimic things that repeat, things that oscillate. So it's nice to have as many tools as we can have, and they just play together in these really interesting ways. So let's move to the tablet, and we'll take some notes on kind of the algebraic representation of these connections. I'll drop this link for you to play in the lecture notes. Okay, so let's jot up some of the definitions and identities we had, just seen graphically. So we said that tangent of theta is equal to sine of theta over cosine theta. We know that cotangent of theta is really equal to 1 over the tangents, the reciprocal of tangent. So what that means is you can always break it down, and I'll say this over and over, you can always break it down to sines and cosines, the kind of Legos of this whole thing, to get that, oh, this is really 1 times the reciprocal of the bottom, which is cosine theta over sine theta. And so we know this is the cotangent-tangent kind of pair of definitions here. When we break it down to sines and cosines, we know that sine of theta is really equal to cosine of theta minus pi over 2. And another way to write that too is cosine of pi over 2 minus theta, which is equal to negative sine of negative theta. Now, I'm going to prove that last bit there. But let's write it down first while we're here. So cos theta, another way to write this is just sine shifted over by pi over 2, which is equal to sine of pi over 2 minus theta, which is equal to cosine of negative theta. Okay, so how we got these last ones, I'll show you again by sketching out a graph right now. So if we start with the unit circle and we take some point up here, for this angle theta, and the point's coordinates are cos theta, sine theta, right? We know that the height here, this is equal to sine theta. What this string here is saying is that that height is equal to, if you took this angle and subtracted off 90 degrees from it. Okay? So if we took this angle and subtracted off 90 degrees from it, and then took the cosine, the horizontal distance, it would be the same. So where would that angle be? Well, theta minus 90 degrees, right? It would form like 90 degrees this way. So it'd be down here in quadrant 4 somewhere. And what they're saying is that this horizontal distance, not that, but this here, which is the cosine of that angle. So here's, theta minus pi over 2. The cosine of that angle is equal to this height. And the same for the cosine, the horizontal distance of 90 degrees minus theta. So where's 90 degrees minus theta? Well, 90 degrees minus theta is this angle here. So here's 90 straight up and down. Minus theta is, this is getting a little sloppy here, but like this angle here. Right, if we took that same amount theta and rotated it back, it's saying that the horizontal distance there, really this should sit on top. I'm just freehanding it. This should sit on top. So that angle is really pointing up to here. So this angle theta minus, or pi over 2 minus theta, this has the same horizontal distance as this has height, this initial one. And it's the same as the other. And then why is this equal to, then the last one, negative sine of negative theta? Well, let's think about this. So we might need a new circle for this. So if my original was up here with theta, and a rotation of negative theta would be coming down here this much. Here's negative theta. And then negative sine of negative theta. Well, let's see. What's the sine of negative theta? Well, the sine of negative theta is this length here. Right, and again, it's not length, it's really the position from. So whatever this length is here, and so the sine is this length, and what is that equal to? It's equal to this length flipped up above. All right, so if this here is given sine theta, this is telling us that this is all equal to negative sine, let me see this. If this piece here is equal to sine of negative theta, then what we had originally must be equal to the opposite of that. Now again, this is kind of windy logic because we're working around a circle. It is literally cyclical. And we have that up there. But you can see how quickly these things are going to kind of keep hitting each other or keep identifying with each other as we work around. So let's do one with a concrete example, because I know chasing variables can be a bit much for too long. And then we'll proceed. So we'll write sine of pi over 6, or 30 degrees, in the 3 different ways using identities, and then we'll verify it graphically. So we know that sine of theta is really equal to cosine of theta minus pi over 2. So that tells us that sine of pi over 6 is really equal to cosine of pi over 6 minus pi over 2. Which is what after we simplify? Well, this is cosine of 1 pi over 6 minus 3 pi over 6. So that's negative 2 pi over 6, which is really cosine of negative pi over 3. So that's the cosine of negative 60 degrees. So let's see, does that make sense when I graph this? It's nice that it corrects my cruddy circles. So the sine of pi over 6, so if I come up 30 degrees, that's like here. This height is the sine, and it's equal to the horizontal distance of a rotation of negative 60 degrees. So negative 60 is something like this, right? So negative pi over 3. And it's talking about the horizontal distance. So this distance here is the same as this distance here. That's what it's saying. And so we can continue with the other parts of this identity, which we said that it's also equal to cosine of pi over 2 minus theta. So pi over 2 minus theta, in our case, pi over 2 minus pi over 6. Again, we're going to get cosine of positive pi over 3, which makes sense geometrically, right? If we did, again, a rotation up of 60 degrees, or pi over 3 in this direction, we're going to see that this horizontal distance is the same as well. And then lastly, we said it's equal to negative sine of negative theta. So that's equal to negative sine of negative pi over 6. So there's 1, 2, 3 different ways. And how does that line up? Well, negative pi over 6 is the rotation. Let's draw a new circle here. Kind of missed our origin, didn't we? Who's the we in that sentence? I did. So negative pi over 6, which is negative 30 degrees, about down here. And it's saying that this value is equal to the opposite of the vertical distance, right, which is this guy here. And that makes total sense if our original was right here. It's just taking that and then flipping it up over the x-axis. So that's that negative piece there. Okay, so we see the algebraic and the graphical here, all stemming from the idea that really sine and cosine are just the same curve shifted over by 90 degrees. So without going into, repeating myself over and over, the same holds for these, obviously, and you can work that out yourself. It's just going to be rotated 90 degrees. So the last one that I want to cover is what's called the Pythagorean identity, and I'm saving it for last because I think it's the most important. These are definitely helpful. I'll say in general, this is used a ton, and knowing these first two is really, really key. To not have to look at a table to know these will help you greatly, reducing your cognitive load in a complex world. But this last one is the most important that you memorize. And I'll give it to you as succinctly as possible. Triangles and circles, fundamental shapes. They are very closely related. All right, we're just going to leave that there. Nope, can't live with it. Can't live with it. Okay. So, for a point xy, which is given by cos theta, sine theta on the coordinates, as long as the radius is 1, right? So here's the deal. For any given theta, the height's given by sine, the width here, we can call it. I didn't know I could get an arrow like that. That's interesting. The horizontal distance is given by cosine. This is a triangle, is it not? It's a right triangle, and it's inscribed inside of this circle. And we know that the radius is equal to 1. So what this tells us from the Pythagorean theorem is that the sine squared of theta plus the cos squared of theta, this length squared, equals 1. So, right, whatever this length is, if you called it, A, you called this one B, and you called this one C, C's in red, you call this one C, we know that A squared plus B squared equals C squared. Well, here we have it, but in terms of sine and cosine. So this is really nice, and you can verify that this is always the case, and I'll give you one quick example. So if we start with sine squared of, let's say, take theta equals pi over 4, not pi equals. Theta equals pi over 4. Sine squared of pi over 4 plus cos squared of pi over 4 equals 1. I chose this because I can show it by hand, but you can really do this with any angle. So sine squared of pi over 4, what does that really mean? Well, this is really, I don't want the equals there. This is really sine of pi over 4 squared. That's what this notation means. We know that sine of pi over 4 is 1 over radical 2. We know that cosine of pi over 4 is 1 over radical 2. So 1 over radical 2 squared is a half, plus a half equals 1. So it works, and again, you can use this for any angle theta. And not only is it nice to kind of be able to show that, but we can manipulate this particular equation in a bunch of different ways. And again, when it comes to problems in calculus, problems in geometry, being able to re-represent things in a simpler way takes a problem going from near impossible or straight up impossible to very doable. So I want to do a bit of work on this right now. Equivalent forms. So knowing and starting off with this fact, which again I highly recommend you go in and verify yourself that this is the case with just a few angles. We know that if I subtracted sine squared from both sides, I would get a new version of this. So cos squared equals 1 minus sine squared. We use this in calculus to change something that's given in cosine to be now in terms of sine, and vice versa. Sine squared theta is equal to 1 minus cos squared. The other thing I can do, because that's all about I can do with just sines and cosines, I can take this whole thing this whole equation and then multiply it by something that I want to multiply it by. So I might multiply this whole thing by 1 over cos squared theta. Why would I do such a thing? Well, if I do that and I distribute that through, one over cos squared theta, what do we see happens? Well, this reduces to 1. Sine squared over cos squared, well, this is equal to tangent squared. And what is 1 over cosine squared? That is secant squared. So this is another form of the Pythagorean identity. And it's used if I want to represent secant in terms of tangent or the other way around. So I could subtract 1 from both sides and just get another version of this. And these 2's are getting a little big. This is really squared. This is not 2 theta. Again, this notation, sine squared theta, what it really means is whatever the sine of that angle is squared. And that follows for all trig notation. It's some of the most debated notation out there. It's not perfect, but it does the job. The last form is if I start back with my original. And what would you want to do now? What's the next logical step? I could take this and multiply it instead of 1 over cosine squared. This is what mathematicians do all day, by the way. Hey, what if we did this? What would happen? Multiplied by 1 over sine squared, we'll get 1 plus cotangent squared theta equals 1 over sine squared, which is cosecant squared theta. And so then from there you can get another version, which is, all right, let's say I have cotangent and I want it in terms of cosecant. There we go. Let's say I wanted it just in terms of sine. Well, I could then say from there, I have cotangent squared. This is really 1 over sine squared theta minus 1. What if I really wanted that in terms of cosine? Well, I could rewrite that as 1 over
1 minus cos squared theta minus 1.
And then, hey, I don't like how that's a fraction and a whole number. Well, I can go in and play with that some more. But you can kind of go around and around and around and move these things into a form that works for you, which again, super, super helpful when you are working with differential equations, derivatives, integrals, which again all come up in calculus. So when you really start to do analysis on these functions and play with the ways that they change, which gets complicated, so you need a big tool belt. Okay, so this is just things to put in your tool belt. But I wanted you to understand where they come from geometrically, as well as how they're related to each other algebraically. So don't be afraid to sketch a bunch of circles, a bunch of the periodic graphs, and get your hands dirty with these. There are some pretty tricky problems in this section, so don't be afraid to put them out in the class discussion. We can work through them together. But really, it's just attacking these ideas from different perspectives so you get comfortable shifting from function to function. Okay, so have fun, enjoy the puzzle of these things and working with these fundamental kind of ideas from math, and we'll see you next time.